everyone.
Good afternoon.
Today I would like to talk about the asymptotic method in models of infection diseases. So, I divided the topics in 4 parts. In the first part, I'm going to talk about the standard susceptible infective model, so SI model. And we want to add special dependence for the SI model, so we show that in the second part by using the step-unit context model, it's called DC model. And in third part, I will talk a little bit about the traveling wave speed for DC model. And finally, we talk about the traveling wave shape for DC model and making the approximation for the shape by using the perturbation expression. So, first for SI model, here we assume the standard SI model without birth and death. And in this model, we divide the population in 2 groups. The first group is the susceptible individuals, denoted by S of T, and infective individuals is denoted by I of T, and all those is dependent on time and greater than or equal 0. Those people leave the susceptible class for the infective class at a rate proportional to the product of the number of infective individual and the number of susceptible individuals. This rate is called the transmission rate. And for total population here, it is constant, and it is the summation for the two groups because our model without birth and death. From the diagram, we see that the changes happen in S. There is some individual leave S and goes to group here I, and that gives us a system of differential equation for the rate of change happening in S and I, just dS by dt is equal minus beta Si. Here minus because S is decreased, and this amount comes to class of I, so it's coming by plus. Here for our model SI, we can represent it by some diseases like HIV, because if you get the infection, you cannot get recovery again. There is another models like SIR. Just here we cannot make additional subgroup R of T. So yes, the recovery individual, and those people here we can get recovery and not get again the recovery for whole their life. Like if we like this diseases, chickenpox and shingles. The other model SIRS, this additional group, subgroup here is the S of T. It's those people who lost their immunity and come back again and get the infection. For example, if you get flu or malaria or meningitis. Let me back for our model SI. For SI here, if we substitute from the total population equation, S is equal M minus I. So we can get the first dimension logistic equation. This equation just depending for I. And we can solve with this under the initial condition when T equals 0, we get I of T is equal, I of T is equal, I of 0 is equal I naught, we get the solution. If this is a logistic curve, and if it is I naught is not equal 0, then when T goes to infinity, we can get I of T goes to M or whole population, and that is, it is clear from the graph here. If we get we have 1,000 people, all the people, if the susceptible is 1999 people, and we have a 1 person infected, you can, when T goes to infinity, we show that the graph is reach the all end. So now for distributed context model, DC model, here at each location S and omega, here omega just the region, small region, some like village or small town. We see the individual is the susceptible class for the infective class at the rate of proportional to weighted average of number of infective individuals and some domain omega, and the density of susceptible at x. For here we let equivalent s xt of xt is dependent for the space and time is the density of susceptible individual, and also I is the density of infection individual. And if we assume it's a population constant, is a population density is a constant for all x, we get the n is equal to summation for the two classes susceptible and infected. So equation 3 here, by substitute I by this integral, it becomes this equation. This equation is called integral differential equation. And this integral here, it is a weighted average over the spatial domain. And k of kxy here, it is called the kernel of the integral differential equation, and is the rate of infection at x by infective at y. And here in this model, the people not living from the location to other location, if we have a two location, so the infective in location x is not moving to location y. So here the infection move it by another contact, by wind, by anything like that. And we find the constant solution for our model is I equals 0 and I equal n. Now for the third part, I will talk about traveling wave speed a little bit. For traveling wave speed as general, we mean that the solution for equation 4, this equation, we get it, is for the form of I of xt is equal a is minus theta x minus ct, where c here is the speed of the traveling wave, and it's not dependent for the x and t separately, but dependent for all the combination above. And if we see here it is greater than 0, we get the traveling wave speed going to the right, and if c it is negative, we get the traveling wave speed go to the left. And we assume that our ribbon is a linear real line here, and here kernel is a conclusion kernel, then by depending for the distance between x and y, and we denote that by k of u. And we have if we say that kernel is symmetric, that means the kernel is a even function and satisfy k of u is equal to k of minus u. And for our analysis, we need to the moment generating function is defined by this integration for the kernel, and we will use it. The Laplace kernel is defined by this amount, and here the Laplace kernel is the symmetric kernel. Now, to compute the traveling wave speed, we'll do that over the linearized equation. When we linearize the DC model, governing equation for DC model, equation 4 that is above, we got it about the solution when I equals 0. So that is give me just, when we substitute I here is equal 0, and we get this equation. And by using the traveling wave and such, or the solution above what we got it for the traveling wave, is equation 5, and make some computation, I will get the characteristic equations. Theta c is equal to beta n times this integral. And this integral from the moment generating function, when substitute x minus y is u, I will get this just is the m of c, for moment generating function. So I get here c, it is equal by divided theta, I divided both sides by theta. This said theta of c, c of theta is equal beta n m of theta over theta. So this is the law for the speed. And for the nonlinear equation, every time we have a two speed. One speed is go to the right, and another speed is go to the left. For right speed is denoted by CR, and it is the infimum of the m of theta over theta when theta greater than 0, and the left speed is denoted by CL, it is the supremum for the m of theta over theta when theta less than 0. And here the kernel is symmetric, so we get the same speed for the left and right. Just CR it is equal minus CL. because the same but in the different direction. But if the kernel is not symmetric, we will get the different speed. Maybe depending if there is wind or something, we will get one of these speed is go faster than another one. And this figure here, it shows us the traveling wave speed go to the right for the DC mode. It have the same speed and the same shape. Nothing different. So the main part here, we need to approximate the traveling wave shape for the DC model, and we will use the perturbation expansion. Here, if we let Z, it is equal S minus T, is the traveling wave coordinate. So equation for the leading equation for the DC model, when we substitute I of x t is equal Iz, it becomes this equation 6. And if we assume it here, the speed is very large, and if we scaling the wave coordinate by zeta is equal z over c, and define new function e of zeta is equal I of z. So the integral in 6, this integral, if I substitute z minus y is u, I will get this integral. So, and when I use the definition of g, I translate I to g, integrated for zeta and u over c. So by using the Taylor series for the g here, I can make this expression for it up to order 1 over c squared. So by take the integral for each part here, each term, for the first term, e of zeta is constant, not dependent for u, so it is constant. The integral for k of u du, and k of u here is the probability density function. So integral of k of u du over r is equal 1. So this first term will give me e of zeta, and the same thing for the last term. In the second term, we get e prime over c is constant, so the integral of uk of u du, it is equal, this is same for the first derivative for the moment generating function. So I can, when theta equals 0 here. So I can replace that by m prime of 0, I will get the approximate series for that integral is half. This is the order up to order 1 over c squared. So when expand e of zeta in powers of 1 over c, then I will get this expanded e of zeta up to order 1 over c squared. So when I use it, equation 7 and 8, and substitute all this at equation 6, and solving this equation, collecting the power of 1 over c, we will get the solution for I of z. It is equal this term, this expansion. So this is the first one is the first term or leading term. The second term is the order of 1 over c, and the last term is the order of 1 over c squared. But here, this is our approximation for the shape, traveling wave shape. But for the symmetric kernel, we find m prime of 0 is equal to 0. The moment generating function, the first derivative, because the kernel here is even, but the first derivative is the odd function. So m prime of 0 is equal to 0. The first term of order 1 over c is cancelled. You can get that perturbation solution. The first term here, the leading term doesn't change, but we got after that the term of order 1 of c squared and up to order 1 over 4, so shift to power 4. And from the figure here, that shows us the solid line is a numerical solution of the traveling wave shape for the DC model, and that line shows us our approximation to order 1 over c squared, but that is for the symmetric kernel. Just we draw it the leading term. Because the first one or first solution for non-symmetric kernel, but for symmetric kernel up to order 1 over 3, but this shape up to order 1 over 4. So just the field leading there. And this one, C is equal to, it gives us the Y good shape. So if it is C, go to the big, get number bigger than 2, we will get approximation better than this. So just to remind you what to do. I talked about the SI model and DC model and how we can calculate the speed for the DC model, and the main part is how to use this perturbation expansion to approximate the traveling wave speed. And finally, I got all this material from the paper for Ian and Mark. So it into the differential equation all are new. And I want to thank the Dr. Michael for this